This is one of the things I finished the slides and said, "Oh, wait, this is supposed to be about microgrids." We have looked at some of the reasoning behind the business cases for making changes and why the Texas grid failure. And John said, "Could microgrids have helped?" And I thought, damn. So I spent 2 days building up a bunch of things and getting it wrong and then rebuilding it again and was, thinking very wonderful thoughts about John while I was doing it. And he was right. It was a lot of fun. I enjoyed doing this. So microgrids are more resilient to the local needs and can be sized to support the community. Where the problem is the federated, complex, interconnected connected grids cannot. They can't react quickly. And as I said, since no one can actually impose their will on the things, then you can run into problems. And the failure of one system can result in a cascade failure of the entire network. The other thing, I had a old IEEE Spectrum uh, magazine that I kept all around for some odd reason from back in 2004. And they did advanced mathematical modeling and suggested that the larger the grid, the more likely it is to fail and with more catastrophic results, which is why when everyone said Texas should connect to either the east or the west grid or both, we said maybe not. Okay, so here is your microgrid architecture, and these are the things like generators, distribution, substation, transformers, all these different elements. And if we jump inside of this microgrid architecture, we're looking at all the different interactions. So we have multiple substations with multiple energy storage system, and the electricity goes back and forth here system control, and we've just centralized it. So again, you would have something connecting or controlling each one of these things with probably an oversee or some sort of governance or even distributed here. Your cyber criminal is inserting malware pretty well everywhere if he can. And also looking at the types of customers, household customers, and of course, again, if you've worked in distribution systems, your critical customers such as hospitals, fire departments, police, so on and so forth. And so I've just modeled some of these things and looked at the inputs and the outputs. But here's the key thing. You can control your external interfaces, and you can also make sure that your generator's distribution, all the rest of the elements in this microgrid are sized so that that way, when you get worst case situations, you can continue to generate. And if you have to, you can do some load shedding and cut off people, but keep your critical customers and other things going. Also size your energy storage so that that way, if it's a temporary thing, you can bring that back on. Also, the fact that you have a lot of cogeneration going on here. So maybe that can help get through some of these things. But with your network of microgrids, you could have energy going back and forth between all of these. But if that one fails, or it has some catastrophic thing going on, you can throw the breakers on your external interface to everybody and say, okay, I'm going to wait till things calm down, and then I'm going to connect up. In other words, it allows each individual grid to support its customers as necessary. We're going to cooperate as much as we can to ensure excess power is consumed, network stability is met, so on and so forth. But when we get a problem, we can say, okay, open the breakers, and we are still a viable system. So if we were to rearrange things rather than we've got lots of transmission lines and everything is connected to one another, in other words, one huge grid of interconnectivity, we say each one of these systems is a self-contained system. And again, I know we will likely have more than one external interface, but I kept it simple. Then this will give us much more resilience into the future. It also means you don't have to have as many large transmission lines.